Hello everyone. In this video lecture, we are going to see the spherical coordinate system, its metric parameters, and the forms of differential operators in spherical coordinate system. In the previous class, we discussed the rectangular and cylindrical coordinate systems as the parts of special curvilinear coordinate systems. This spherical coordinate system is the third one, where a point P in a three-dimensional space is described using the coordinates r, theta and phi. We know in curvilinear coordinate systems, we use the generalized notations u, v and w. Here r, theta and phi, they are u, v and w respectively. So to describe this P, let us consider the Cartesian coordinate system with the x, y and z axis, O being the origin. Now let's join this point P and the origin, that makes the line OP, or we can say the vector OP vector, the position vector R, the magnitude of the position vector is R. The distance of the point P from the origin, that is R. And theta is the angle of this OP from the Z axis. It is also called as the polar angle. And phi is the angle that is swept by the projection of OP. OP can be projected on the XY plane so that we get OM. And the angle swept by this OM from the x-axis, that is described as phi. It is also called as azimuthal angle. So the radial distance r, polar angle theta and azimuthal angle phi, they are used in spherical coordinate system. To find the transformation equations, let us use the next figure. In the first figure itself, I have marked the unit vectors E1, E2 and E3. As mentioned in the previous class, E1 vector that corresponds to R. So its direction can easily be identified as the direction of R. As R is the radial distance, E1 is the vector that can be drawn at the point P, pointing towards the radial distance R. So it is E1 cap. And E2 corresponds to the polar angle theta, where theta is the angle made by OP from Z axis. Right? So this OP, the OP, it makes angle from Z axis. So it can be along this curve segment. And the tangent you need to consider from the point P. The tangent of this circular segment pointing from point P, that forms E2. Similarly, E3 cap, it corresponds to the azimuthal angle phi, which is the angle swept by OM. So in the horizontal circular section, the tangent of this section should be drawn at the point P. So the tangential vector that is drawn at P, that is E3 cap. And in the second figure, we can consider some geometric parameters through which we can find the transformation equation. The same point P and the projection all are drawn. The OP distance is R. This OP vector can be resolved into two components. The one along Z axis, it is R cos theta, it is named as Z. And the other component, it is R sin theta, right, that lies along OM, and let us name it a rho. So the two components of the position vector are r cos theta and r sin theta in z-axis and along OM respectively, and we name them as Z and rho. And once again, this OM vector, which is named as rho, is resolved into two components, one along x-axis and the other one along this z-axis. So when you resolve this r sin theta into two components, we get the sine component of this rho. Rho sin phi along z direction and rho cos phi along x direction, right? So what is x now? X is the distance from O to this line. So x is nothing but rho sin phi. So rho can be expanded as r sin theta. R sin theta cos phi is x. And y is equal to r sin theta sin phi. That means it is rho sin phi. Rho is expanded here as r sin theta. So y is equal to r sin theta sin phi and z equal to r cos theta, the vertical distance. So these are the transformation equations. From the spherical coordinate system, we can get the rectangular Cartesian coordinate system. And the reverse is also true. Using these three equations, we can use the transformation from rectangular system to spherical system also. For that, we know r it is the magnitude of the position vector. So we can very well write square root of x square plus y square plus z square. And to find theta, we can use the third equation, z equal to r cos theta, where you can find it as cos inverse of z by r. Cos inverse of z by r is the magnitude, which we already know as a square root of x square plus y square plus z square. That is what substituted here. And to find phi, we can use the first two transformation equations. Sin phi divided by cos phi can give you tan phi. So I am going to divide the second equation by the first one. By doing so, r sin theta gets cancelled. I get tan phi is equal to y by x. So phi is equal to tan inverse of y by x. So these three equations are the transformation equations which are helpful to transform the rectangular coordinate system into spherical coordinate system. So now to find the metric parameters, we are going to follow our usual method, how we did for the rectangular and cylindrical coordinate systems. We know ds square is dx square plus dy square plus dz square, which we take as equation 1. And we will expand this for the particular system, that is a spherical coordinate system. And finally, we will write another expression for ds square in terms of metric parameter. We will compare the two equations and thereby we will get the metric parameters. That's what we are going to do now. We know the transformation equation x equal to r sin theta cos phi. And the differential operator, we can take the differentiation of this x in terms of partial differentiation. We can write dou x by dou r. X is a function of r, theta and phi. So the differentiation can be written as dou x by dou r into dr plus dou x by dou theta d theta plus dou x by dou phi d phi. So I find the partial differentiation of this x with respect to r, that comes as sin theta cos phi and dr, because theta and phi can be treated as the constants when it comes to partial differentiation. I differentiate only r, so I get dr. The same way, for the second term, I am differentiating this x with respect to theta, partially differentiating with respect to theta. So I get r cos phi cos theta d theta, because I can differentiate only sin theta, cos theta d theta. And then the third term, it is dou x by dou phi into d phi. So differentiating with respect to phi, I get minus sin phi. So minus r sin theta sin phi and d phi is written. And next, for equation 1, we need a dx square. So I'm going to take square of this equation. A plus b plus c the whole square formula I can apply, and I get this expression just expanded using the formula. So I get 9 terms, and I name this as equation 2. Similar way, I am going to write the transformation equation for y. Y is r sin theta sin phi. We know the definition for dy in terms of partial differentiation. It is dou y by dou r into dr plus dou y by dou theta into d theta plus dou y by dou phi d phi. Using this y expression, I am getting dy. Partially differentiating this y with respect to r, it gives you sin theta sin phi dr. And then for the second term, I am differentiating partially with respect to theta. I get r cos theta sin phi and this d theta, plus differentiating partially with respect to phi, I get r sin theta cos phi and this d phi is written. I get this expression as dy. Take the square of this dy using the same formula a plus b plus c the whole square. I expand it and I am getting an expression with 9 terms, and I name it as equation 3. We are going to do this for z also. The transformation equation for z is r cos theta, and we know dz is dou z by dou r dr plus dou z by dou theta d theta plus dou z by dou phi d phi. By taking the partial differentiation for r and theta, z is not a function of a phi, so the first 2 terms alone we get cos theta dr minus r sin theta d theta. And by taking the square of this, we get a minus b whole square formula. Using it, we get this equation 4, by squaring it. And we know ds square is the sum of dx square, dy square and dz square. So write all the terms, take the summation and simplify wherever possible, because we have plus and minus signs equal same terms with plus and minus signs. You can cancel them, and finally that expression reduces to this format. d square becomes dr square plus r square d theta square plus r square sin square theta d phi square, and this I call as equation 5. And in the previous lessons we came across another expression for ds square, which in terms of metric parameters, which is h1 square dr square plus h2 square d theta square plus h3 square d phi square. We name it as equation 6. We can compare these two equations. So by comparing equations 5 and 6, I come across h1 square as 1, h2 square as r square, and h3 square as r square sin square theta. So from that I can arrive at h1 as 1, h2 as r and h3 as r sin theta. These are the metric parameters for spherical coordinate systems. You can do the in-between steps also while deriving it. Next we are going to find the differential operators in this spherical coordinate system. Already we know the generalized form for the curve from the curvilinear systems. We know the general equation for gradient. For any curvilinear system, del is equal to this. This is the general form. But now for specific spherical coordinate system, we know what are h1, h2, h3, u, v, w. So by substituting these metric parameters and u, v, w appropriately, we get expression like this. Dou by dou r. In place of u, I have written r, and h1 is 1. So we get dou by dou r E1 cap plus h2 is r. So we get 1 by r dou by dou theta E2 cap plus 1 by r sin theta, which is h3, dou by dou phi E3 cap. So this is the expression for gradient in spherical coordinate system. The same way we can do it for the divergence also. In the curvilinear systems, we derived expression for divergence as this. Del dot f is 1 by h1, h2, h3 and dou by dou u of the scalar function f1, h2, h3 plus the other two terms are similar. Here also, when you substitute the appropriate values of the metric parameters and u, v, w, we get exact expression for divergence in spherical coordinate system like this. So 1 by h1, h2, h3 gives you 1 by r into r sin theta. So we get r square sin theta, 1 by r square sin theta. And inside the bracket it is dou by dou r f1. F1 will be the first component of the vector. R square h2 h3 is r square sin theta plus dou by dou theta of f2 r sin theta plus dou by dou phi of f3 r. So this is the expression for divergence in spherical coordinate system. For curl, we know the general expression from the curvilinear system. Here also replace all the metric parameters and u, v, w with appropriate values or expressions. We get curl like this. Del cross f is 1 by r square sin theta. Determinant of the matrices with the row elements as E1 cap or E2 cap or sin theta E3 cap. Dou by dou r, dou by dou theta, dou by dou phi in the second row. F1, F2r, F3r sin theta in the third row. Next, you can apply whatever we read in the previous lessons. You can apply and we can do a few of the homework problems given in this lecture. Derive Laplacian operator in curvilinear coordinate system and then find the same in rectangular, cylindrical and spherical coordinate systems. In curvilinear system, we have derived the expression for gradient del. So Laplacian operator is del square. So del dot del gives you del square. So try to find del dot del and then you find specific expression for the three special coordinate systems. Try this out. Next, this is very simple. You know the transformation equations. Transform the Cartesian coordinates 1, 2, 3 to cylindrical and spherical coordinates. When you know the transformation equations, you can easily transform one coordinate system to another system. So here, rectangular system is given. Using the appropriate transformation equations, find the cylindrical and spherical coordinates. Very simple. And the last one is find the Cartesian coordinates of the point whose spherical coordinates are these. So here spherical coordinates are given. You are supposed to transform them into rectangular Cartesian system.